Welcome to this lecture. This was part of our winter school that we just completed last week, as recent as last week, and the focus here was during this physics lecture was momentum, collisions, work, energy, and power. So the idea here is to cover all the basic theory, the concepts, as well as problem-solving techniques involving this section over here. So at the end of this video, you should be able to tackle questions on momentum, collisions, work, energy, power, as well as apply the work energy theorem. So lots of fun, lots of exciting stuff. So let's get on with it. So I think it's very, very important to note that the definitions are so crucial for any section, be it chemistry, be it physics. So I would always recommend that you have a little notebook and make a note of all the definitions, all the laws that you actually learn. So for instance, we look at the definition of linear momentum. That's very important. Look at some everyday examples arising from that definition. Then look at the concept of impulse. How is the impulse related to Newton's second law? And of course, the conservation of linear momentum, and added to that, the conservation of energy with regards to what we call elastic and inelastic collisions. So yeah, what's cool about the video is you can pause it if you're ever stuck or you need some sort of confirmation of concepts. Do not move on to the next slide if you're not sure of what's happening. So it's important that you understand before moving forward. I think that's key to actually using these videos. So let's move on. Okay, what is momentum? And everyone would tell me that the momentum of an object is really, let me just write this down and see whether it makes sense to you. So P is equal to M times V. And from there we can get the definition that the momentum of an object of mass m moving with a velocity v is just the product m times v. And you notice very quickly that momentum is a vector quantity. This is very, very important as well. So when you're dealing with problem involving momenta, the plural, you need to take into account direction. So your knowledge of vectors has got to be really solid when working with momentum. So momentum is nothing more than the product of an object's mass and its velocity. What is the unit for momentum? So if you look at the unit for momentum, so here I'm writing just the scalar, or what we call the magnitude. So I'm dropping those arrows. So this is now a scalar, or let me write this as magnitude. Physicists are very, very particular in the way they write things, especially as well as mathematicians. So without arrows above P and V, we're looking at the magnitude. And look at how I spell magnitude. Oh my goodness, please write neatly. And the units for momentum, let's put this in square brackets, is the mass, which is kg, and velocity is meter per second squared. And there you have it. Please, I must emphasize, working momentum, direction is very important. Conservation of linear momentum. The total linear momentum of an isolated system remains constant in both magnitude and direction. Very easily stated. You can learn this without understanding it. So firstly, what is an isolated system? An isolated system is a system that doesn't interact with the rest of the universe. Isolated. So its absence, or basically there's no external influence. That's essentially what we're saying. I would say linear because we also speak of angular momentum. So make sure when you are stating a law, state it precisely. Okay, just don't. The total momentum, the total linear momentum of an isolated system remains constant in both magnitude and direction. And you would have seen, like, in summary, that the total linear momentum before collision equals to the total linear momentum after collision. That's not really a good statement of the conservation of linear momentum. The one that we have here is beautiful, beautiful. Right, so speak of collisions. Before that, it's like, yeah, why do we need to study momentum? And you'd find that momentum plays a very important role in everyday life, from cricket to football to collisions. It's absolutely vital that we understand how momentum actually intertwines itself into our daily lives. So a collision between, say, ball and bat, one could understand, one could predict, for instance, the resultant speed, the distance, just by observing what happens during a collision. So firstly, let's look at a very particular case of collisions and what we call an elastic collision, which is an ideal collision. And here we'd say very simply that the total kinetic energy of the system before collision is equal to the total kinetic energy of the system after collision. All right, so that's also very, very important. So momentum we know is conserved, and we know that for elastic collisions, we have kinetic energy also conserved, and I think that is crucial. So let's just keep those in mind before we start looking at a problem involving collisions. So what's an inelastic collision? So if a collision is not elastic, then it's inelastic. If you have a look here, we define a collision as two objects striking one another. We know that. But more important, the time of collision, the interaction time here is really, really small. And the inelastic collision, basically momentum is conserved but not kinetic. So what actually happens if you think of two snooker balls or two billiard balls colliding, boom! Some of that energy is going to be lost in the form of heat, or what we would call sound energy. So there's energy lost, and hence the total kinetic energy before collision is not equal to the total kinetic energy after collision. And something interesting here as well, a completely inelastic collision is when objects stick together after they collide. You'll see a lot of exam questions if you go over past papers based on such problems. So what I want to do next is to actually now write down mathematically what we mean by conservation of linear momentum, as well as the conservation of kinetic energy during an elastic collision. So let's put in some mathematics. I know some of you try to shy away from mathematics, but remember, mathematics is a beautiful, beautiful language using beautiful symbols. So let's get stuck into it. Okay, so let's look at the case of elastic collisions. The moment I see that, I can quickly write down, and hopefully you agree with me, that the momentum before collision equals to the momentum after collision, right? And how would one express that mathematically? So let's think of a two-body collision, which is very common. With three body, then we'll just extend the number of masses. So for a two-body collision, we can easily write in a beautiful purple the mass m1, the initial velocity v1i, plus m2 v2i is equal to what? m1 v1 f, v1 f being the final velocity of object 1, plus m2 v2 f, where v2 f is the final velocity, well, after collision of mass m2. Now, in the same breath, let's write down kinetic energy. So I would say ke initial, or some people say ek, is equal to ek after. And what can we write down mathematically in this beautiful blue? Kinetic energies are half m1 v. This is very bad notation. I've never understood why they use such a messy notation, but they use it. Initial velocity, kinetic energy of 1, mass 2, and then you got final velocity, kinetic energy m. Sorry, that should be a 1 v1f squared, too many subscripts and superscripts, but we master this as we do lots and lots of examples. So that's basically, for inelastic collisions, you can write down those two equations and they're always satisfied. Awesome! Inelastic collision. So we know an inelastic collision, then we know that the momentum before equals to the momentum after, just like elastic collision. So we can write mathematically m1 v1i plus m2 v2i is equal to m1 v1, write neatly, plus m2 v2f. All right. But what's not conserved, do you remember that, is that the kinetic energy before collision is not equal to the kinetic energy after. And we know that energy is lost in the form of heat. And people talk about sound. Bang, to really? Yes, really. So inelastic collision, just be careful. Kinetic energy is not conserved. Then you have the case of a completely elastic collision where if the two objects stick together, stick together, then you would recall that the final velocity v1f must equal to v2f, and I like to call that v. We'll come across problems like that, but just keep that in mind. This is a beautiful, beautiful blue. In fact, I love this blue because you don't even know it's black or blue. That's the mystery. Anyway, let's go on. Okay, what have we here? A 10-gram bullet moving horizontally at 375 meters per second penetrates a 3 kg wood block resting on a friction horizontal surface. If the bullet slows down to 300 meters per second after emerging from the block, what is the speed of the block immediately after the collision? So, we could say before collision, what's really happening? There's the bullet. Don't get too fancy with your drawings. It's about the physics, right? So M1 is 10 grams. Straight away convert that to kgs. The bullet is moving V1I, it's 375 meters per second. The block M2 is 3 kgs, and obviously V2I is 0 meters per second. That's before collision. What is happening after collision? Do you remember? Can you see, or do you know? Then this block will now start to move, né? And the bullet comes out the other side. So things have changed. So we know that M2, the mass of the block, doesn't really change. The velocity of the block is what they want us to find beautiful. The bullet itself, mass does not change, so it's 10 over 1,000 kgs. And they give you the final V2, V1, because we call that stick with notation. The bullet is mass M1, so it's V1F, 300 meters per second. I'm going to emphasize this, I'm going to choose motion to the right as positive. So we write down momentum before, write neatly again, is equal to momentum after. So that's M1 V1I plus M2 V2I is equal to 1 V1F plus M2V. I'm not sure how many times I've written this equation. A billion times, I don't know, but I always write it. So, M1 we said 10 over 1,000. I'm writing it as 10 over 1,000. You can use your smart calculators and work thus. V1I is 375. Whoa! 375. M2 is 3. Initial is 0. M1, 10 over 1,000 times 300 plus 3 times V2F. And have a look at this. Only one unknown and we can all solve, and there's your 1 mark. Awesome. But it's not just getting the answer, folks. It's about how you lay out the problem. Look at that. Before, after. Write down what's given, what's to be found. Look at that question mark. Choose a direction that's positive. Write down the conservation of linear momentum and then solve for the unknown quantity. I'm yet to find a student that will lay out his work so beautifully and so elegantly. What have we here? 2 balls with mass 3 kg and 6 kg travel towards each other. So let's go with this before. This is so much fun. So they travel towards each other. Doesn't really matter which is sitting where. So there's one ball, let's call that M1, and its mass is 3 kgs moving towards each other. So this one's moving that way, that's moving there. That's what I mean by towards. The other one is 6 kgs. See, they don't even give you, this give you the speeds. That means the magnitude of the velocities. So the 3 kg ball is moving at 12 meters per second. So we'd say V1R is moving at 12 meters per second. And If you look at V2I, now I'm going to give it some direction. So it's going to be minus 4 meters per second. Where did that come from? That came from the fact that I'm choosing to the right as positive. So anything moving towards the left will be negative. So what happens after collision? After collision, it says that if the balls have a head-on inelastic collision and the 3 kg ball recoils with a speed of 8 meters per second, how much kinetic energy is lost in the... Oh my goodness, and this is a beautiful question. So you got a 3 kg ball and it's going to be moving in that direction over there with a speed of 8 meters per second. So they gave you V2F, not V2, but V1F as minus 8 meters per second. You got to stick with my sign convention. We don't know what happens to the other ball, so let's give that M2, its mass does not change, is 6 kgs. So if we want to know the kinetic energy that's lost in the system, we better know how fast M2 is moving after the collision. So I want to squeeze, because all the details in here, I just want to squeeze in this little corner, conservation of linear momentum, and we're going to go something like P before equals to P after, again for the 100 billionth time, but write it down, don't be lazy, plus M2 V2R is equal to M1 V1F plus M2 V2F. M1 V1, it'll be 3 moving at 12 plus M2, which is 6 moving at minus 4 equals 2. 3 kgs times minus 8 plus M2, which is 6 times V2F. That's 36 minus 24. Is that right? 36 minus 24 gives me 12. 3/8 of 24 goes on the other side, becomes 36. So V2F turns out to be 6 meters per second. So let's talk about that. 6 meters per second. That means the 6 kg ball also repels, bang, and it moves in the opposite direction. So the 6 kg ball after collision is moving towards the right hand side. But to answer the question is very, very simple. So I want to squeeze in more details here, but do not do that. I mean, use extra paper and stuff like that. So what we're going to do is, because I want you to have a glance of what's happening here, the kinetic energy before collision is equal to half m1 v1 squared plus a half m2 v2 squared, which is a half times 3. v1 is 12 squared plus a half. m2 is 6 and v2 squared was minus 4. It doesn't matter because you're going to square that. That's 144 divided by 2 times 3 plus that. You can work that in a calculator. It's number of joules. So you do the same for kinetic energy after. So the kinetic energy after collision, now be careful, it's a half m1 v1 f squared plus a half m2 v2 f squared. Put in the numbers, a half times 3 v1 f is minus 8 squared plus a half of 6 times 6 squared. There you have it. And how do you work out the amount of kinetic energy that's lost in the collision? It'll be EK after minus EK before. And there's your 1 mark. Huh? 1 mark? Yeah. There's not a lot of thinking involved here, just a matter of writing stuff down. But please do this problem by yourself and then check your work against mine. New concept. What is impulse? Impulse. You acted on impulse. That's different. Or the perfume impulse. No. This is something different. An impulse is really nothing more than the product of force with the interaction time delta t, or better still, or very simply, impulse is defined as the change in momentum. Now the symbol I use for impulse, here they use an I actually tend to use a J for impulse, and it's delta P. So impulse is a vector quantity, so direction is very, very important. And you'll also know that F delta T, the average force acting over that interaction time delta t is equal to delta p. So there are two formulae. There's one over here. That should be a J. I'd like to call it a J. It's F delta T O M delta V. The units for impulse, interesting. 2 units again. If it's delta P, then the units here would be the same units as momentum. But if you use F delta T, then it's also Newton second. That might be a nice multiple choice question. Impulse, also very important. If you look at this graph over here, a graph plotted force versus time, the area under the graph, let me write that so you remind you. The area under force versus time graph will give you the impulse, right? F delta T. Awesome. That's pretty cool. Now, in everyday life, we see a lot of the applications of this F delta T. In sport, for instance, I keep looking at cricket because of Cricket World Cup that's currently on. If you ever see a fielder catching a cricket ball, he doesn't just stick his hand out there. As the ball comes to him, he draws his hand inwards to basically increase the interaction time, or what people will call the contact time, hence reducing the force. So I just want to look at that concept more closely in the next slide. Want to do is, we've studied Newton's second law in grade 11, and we're going to look at how is Newton's second law related to momentum. So you know that the net force acting on an object is equal to m times a. So another way of writing it is F net is equal to m times a. But if you write this as m, and a is nothing more than delta v over delta t, right? So what we have on the top is m delta v over delta t, and you can write that as delta because m is a scalar. You can write it like this, and then you're going to get m delta v over delta t, which is nothing more than delta p over delta t in terms of vectors. So what I've just written is quite powerful. It tells me that the net force acting on an object, F net acting on an object, is equal to the, I'm going to use this and write this big, rate of change of momentum. Not equal to the change in momentum. Unless you say change in momentum. No. You're dividing by time, so it's a rate of change of momentum, and that's an alternate formulation of Newton's second law. We see a lot of that application always. How do airbags work? So I'm just going to make notes here, and you are going to explore that. So, airbags. So one, think of airbags. How do they work? Right? 2, another thing that's very interesting are what we call arrestor beds. If you're traveling along route, say going up to Pietermaritzburg or coming down Fields Hill, you'll see something called arrestor beds. How do they work? 3, crumple zones. If you look at the very first slide, a car colliding and crash test dummies, crumple zones in cars. How do they work? And also, I want you to try this experiment. Catch an egg. How do you spell catch? C-A-T. Catch an egg with a glass plate. Is it possible? How do you do it? Yes, think about that very carefully. And if you can think of it and even do the experiment, then you'd have a deeper understanding of, and I think this is the very important notion, the notion of contact time and how it's related to the net force acting on an object. So awesome stuff. Please run through these things and make sure you understand each of these points that I've scribbled along here. Okay, cool stuff. Okay, so here's a typical exam question based on a momentum. Notice the marks, 12 marks. Let's have a look at this. Dancers have to learn many skills. Oh, I remember, I was a break dancer way back in the 80s. You would not believe it, but there's so much of fun, absolutely amazing. A lot of physics, popping, waving, electro rock. It has its own genre of music. Not only the music, but the dance moves, as well as even the fashion associated with the break dance and hip hop. It was brilliant. The windmill, spinning on the back, spinning on the knees, spinning on your head. Whoa, awesome stuff. Anyway, let's get back to the problem. A dancer of mass of 50 kgs leaps into the air, yo, and lands on her feet first on the ground. She lands on the ground with a velocity of 5 meters per second. And as she lands, she bends her knees and comes to a complete stop in 0.2 seconds. Calculate the momentum with which the dancer reaches the ground. Hey, hey, 3 marks. Not too shabby. Define the term impulse. Straightforward. Calculate the magnitude of the net force acting on the dancer. Oh man. Can we get anything more challenging here? Assume that the dancer performs the same jump as before but lands without bending her knees. Ooh, painful. Will the force now be... Oh, it's obviously greater. Give a reason to the... Oh my goodness. Simple question, 12 marks. But past paper. Right, let's have a look and write down the solutions. Do not just read and say, I can do this, I can do that. No, write it down. You must write down your answers. Okay, so what are we given? We are given the mass of the dancer, 50 kgs. Her velocity when she hits the ground, I would rather say the speed, because she's moving downwards, is 5 meters per second. And she bends her knees, and you've got 0.2 seconds. So if we look at 4.1, calculate the momentum. Oh man, the momentum P is equal to M times V. The momentum, so the momentum is 50 and then it's 5, which is 250 kg meter per second. And that's down towards the ground. Don't put arrows like this, you must write towards the ground. 4.2, define the term impulse. Impulse is the change in momentum of an object. Write it down. Write it down. I've written this billions of times and I still write it down. And then the next question in this beautiful red. Calculate the net force. Well, F net, it's magnitude, so we don't have to give direction. Magnitude, no direction. It's delta P over delta T. The change in momentum, right? It's just basically she starts from rest coming down there. The change in momentum would be what we calculated here is 250 and over 0.2. So we're going to multiply that out. 5, 5, 25, 5, 1, 2, 5, naught. And I can write this as Newton a second. Not Newton per second, but Newton times second. Correct? And then the last bit, because remember, she is starting from rest and then she hits at 5 meters per second. So V1I is 0, V2F is 5. So delta V is 5 minus 0, which is 5. So we get that. Nicely done, nicely done. And then 4.4, come on, you think about this, eh? It's as if the laws of physics are built into our brain. We know that if we jump off a table or when we hit the floor, we gotta bend our knees. If we don't bend our knees, oh my goodness, it'll be painful. Our kneecaps could pop off. So the force exerted by the ground on us is obviously going to be greater than, oh my goodness, very painful. And then 4.5, why is it painful? Well, we're going to have F net, the force exerted on us by the ground is delta P over delta T. So recall, if delta T is small, if we're not bending, then it implies that F net, oh my goodness, is going to be large. And large means painful. Awesome, 12 out of 12. That's what we want. Hey folks, so what have we here? Another exam question. How many marks? 11. So let's go for 11 out of 11. Diagram below shows two trolleys P and Q held together by means of a compressed spring on a flat frictionless horizontal track. The masses P and Q are 400 grams and 600 grams respectively. So there we go. So before the spring is released, we can see everything's stationary, nothing's moving. So the total momentum before anything happens is going to be 0. If you think of a compressed spring and when it's released, I think of it as an explosion. When the trolleys are released, it takes 0.3 seconds for the spring to unwind to its natural length. That's already the contact time between the two. Release, poof. And that's the time at which the force acts. Is 0.3 seconds. Trolley Q then moves to the right at 4 meters per second. State the principle of conservation of linear momentum in words. Calculate. Okay, so let's take a closer look at this system and this question. So we can see straight away, and this is where I would start. I'll write down what's given, and we are given that the mass of trolley P is 400 grams, and 400 grams is 0.4 kgs. Got to do that. The mass of Q is 600 grams, which is 0.6 kgs. V1I, or we can say V1 or VPI, velocity, initial velocity of trolley P, is equal to the initial velocity of trolley Q, is equal to 0 meters per second. So the momentum before is equal to MPVPI plus MQVQI, and that's a big fat 0 kg meter per second. So the first thing, oh, I even forgot to even read the question. State the principle of conservation of linear momentum in words. So say the total linear momentum, write neatly, of an isolated system remains constant in both, what am I writing, magnitude and unacceptable in an exam to write like this, please. Right, 4.2.1. So 4.2.1, see the velocity of trolley Q after the trolleys are released. So we know that P before must equal to P after. I'm going to choose to the right as positive. That's very important as well, choosing a direction. You must actually state that, choosing right as positive. So we know P before, we already said was 0. It's here. Momentum after would be MPVPF plus MQVQF. The mass of trolley P is 0.4. It tells us that trolley Q moves to the right at 4 meters per second, so VPF plus 0.6. It'll be plus 4 because we chose to the right as positive, and eventually we can write that the final velocity of trolley P will be 4 times 0.6, which is minus 2.4, taken on the other side, or 0.4. And that turns out to be, if I do that right, is it minus 0.6 meters per second? And the reason for that is the negative sign is because we chose to the right as positive. So if we chose to the right as positive, then we know any negative sign tells us that that trolley is moving to the left. So that's my answer there. Okay, 0.4. Hopefully I've got that right. Yeah, one could double check that. That's like 24/4. 24/4. That's more like 6 meters per second. I ended up with 0.6 meters per second. That's a problem. So please check that. It's actually 6 meters per second. I'm not using a calculator, yeah. So yeah, that's 24/4, which is 6 meters per second, and that'll be to the left. And then 4.2.2, we become too dependent on these machines called calculators. 4.2.2, magnitude of the average force exerted. Average force, we've got delta T. So the average force F net is equal to delta P over delta T. We've got the change in momentum, say, of trolley Q. The change in momentum of trolley Q, we said, was the mass of trolley Q, and then it's delta V over delta T. We've got its velocity change. Remember, we're looking at the magnitude, so be careful now of any problems with sign. So the mass of trolley Q was 0,6. Its change in velocity will be the final velocity they gave us was 4. Initial velocity was 0, 0,6, and delta T is 0,3. And that's 2 times 4, so that should give me 8 newtons. Please double check that as well. And the last part of the question, is this collision elastic or inelastic? Answer only yes or no. Now, if there's no friction, there's no dissipation, then the explosion itself, as they get pushed apart, will be an elastic collision. But then some may argue and say, but hey, you know what, the spring may not be, obeying Hooke's law. There could be some dissipation in the spring. As the spring starts to expand, that could heat up a bit and you could have energy loss. But for all intents and purposes, the spring is stiff enough, large spring constant, hence minimal energy loss. So I would go with an elastic explosion rather than a collision. Awesome. 11 out of 11. So those are really cool calculations, but you know what? If you really want to master this section or any other section in physics, chemistry, mathematics, you've got to do lots of problems. You understand the fundamental theory, you understand the concepts, you understand also the formulae, and then problem solving is absolutely vital. Now, before I leave you with the momentum, because I'm going to keep the videos separate, I think they're too long. So this will be the momentum, and then I'll have another video up with work, energy, and power. So have a look here. If I had to plot a graph, just very quickly, of momentum, or maybe kinetic energy on the y-axis versus momentum, what would this graph look like? Would it be a straight line? Would it be parabola, hyperbola? Would it be exponential? Think about that very carefully. It's a very interesting question, this. A lot of students don't seem to know how to make that connection. Well, P is equal to mv. Let's look at scalar. The kinetic energy of the object is a half mv squared. All right. There's a connection between the kinetic energy and the momentum. You can see straight away if you use your knowledge of calculus. If you differentiate the kinetic energy with respect to v, you actually get the momentum. Right, so have I said that right? So d kinetic energy dv is a half to mv, which is mv equal to p. But that still doesn't help me with this graph, does it? The derivative of the kinetic energy. Hey, yes, it does. So that basically means, interestingly enough, that the kinetic energy versus momentum would look something like this. If I take momentum and I square it, I'll get m squared v squared. Looks similar, except there's an m squared there. But what if I divide both sides by 2m? Hey, look at what I get here. mv squared over 2, which is the same as a half mv squared, which is the kinetic energy. So for the first time, most people are seeing this, and that is the kinetic energy is actually equal to p squared over 2m. The fact that it goes like p squared, remember you plotted graphs like y equal to x squared. The shape of that graph, parabola. Nicely done. So the graph of kinetic energy versus momentum would go like that, which is parabolic in nature because the 2m here is actually a constant. Awesome. This is a nice multiple choice question. Which one of the following graphs is the best description of kinetic energy versus momentum? And how many of you would have chosen this graph that I've just drawn over here? And that's how you learn. You just don't just do the past papers, go and get the 80, 90, 100% and then start celebrating. No, you got to understand. You got to put in a deeper understanding so that when you do well, You know, it's a genuine result. It's not just based on superficial knowledge of the subject. Cool stuff, man. So this is our momentum video, and we will be putting up our work energy power video soon.